Okay. So is cybersecurity fundamentally a physics-based problem? And if you're considering that question and you're thinking to yourself that maybe this presentation is going to be a little theoretical, maybe a little abstract, you would be correct. But it's not theoretical and abstract just for the sake of being theoretical and abstract. It's really this way because a lot of what some of my colleagues and I have been trying to understand is, why do we believe what we believe when it comes to cybersecurity? And when we started to ask ourselves this question and really dive in, we ended up at the question of, well, is cybersecurity fundamentally physics-based? And when we started to think about this question, I'm not going to try to convince anybody that cybersecurity is, as a matter of fact, fundamentally based in physics. But what I am going to try to do is convince you all that this question is not nearly as absurd as it might sound. And when we start to think about what we know about physics and what we're learning about physics, and we start to apply it to what we think we know about cybersecurity, it appears that we can take some things that maybe we always thought we knew about cybersecurity and fundamentally ground them and say, yes, this is true, and here's why. While simultaneously taking some other things that maybe we thought we knew about cybersecurity and saying, well, these, I'm not so sure about these, and here's why. And in order for me to be able to explain why I think this, I need to tell a story, and I need to talk about some of the early days of computer security research and some of the early technologies developed in computers and communication, and how those early technologies actually still impact what we do now in modern technology, and the implications that that might have going forward. And all of this really started with a simple observation. And that observation was, we tend to treat cybersecurity as if it's an engineering discipline, but to call something engineering really presupposes that there is a scientific foundation upon which that engineering is built. And it's not obvious to me that we've developed that foundation, right? So that's what some colleagues and I started to really look into. And one of the things that I specifically remember saying at the very onset of this effort years ago was that it didn't seem like cybersecurity was a physics-based problem, so we probably shouldn't be expecting an F equals MA type equivalent for cybersecurity. So now, fast forward several years, I'm now speaking in front of an uncomfortably large number of people, trying to convince them that actually maybe there is a chance. So how did I get here? Well, to understand that, I need to talk a little bit about the early days of computer security research. So in the early days of computer security research, there was a lot of emphasis placed on trust, building trust into computers for security, right? So there was a lot of work in formal methods. So building provably secure systems. And as we all know now, that's very difficult. And there's a lot of questions as to how well that could actually scale. So from trust, it extended to trustworthiness, right? And where trust is a binary, you either trust or you don't trust something, trustworthiness exists on a spectrum. And we place something on that spectrum, and then, based upon where we place it, we decide, should I trust or should I not trust? That also turns out to be very difficult in computer security. So now, a lot of the contemporary research is based on the idea of risk. What risk does something present? And what I would argue is that we can use this progression of research to actually arrive at the fundamental principles of computer security. And let me explain that. So when we think about security, what does that mean? How do we define security? So there are many, many definitions of security, and nobody agrees on any of them, right? So it's not going to hurt if I add one more. So what I will say is that we can think about security as the protection of value. Just very generally speaking, we protect things or we secure things that are valuable to us, right? And if we take that a step further, we find value in things that have meaning to us. So ultimately, I would argue that we can define security as the protection of meaning and value, okay? So in the early days of computer security research, there was a lot of emphasis placed on trust. Why? Why would trust be the first thing that people would think about when they thought about computer security? Well, what were they trying to secure back then? That was classified information. Only certain people are trusted with classified information. And since that classified information started to get put on computers, it started to make a whole lot of sense then why you would want to treat a computer as an agent that also needed to be trusted. So this seems to be an early admission that trust was actually fundamental to security in the early days of computer security research. But like I said, we eventually went to trustworthiness and then to risk. And also, like I said, I think we can use this progression to arrive at a conclusion of the fundamental principles of cybersecurity. So just like the research progressed from trust to ultimately risk, can we make a logical progression? And can we reason our way from trust to risk being the more fundamental concept? And I would say that I think we can, because if we read what people have written about the idea of risk and trust from those that think about things like risk and trust, what we read is that situations that involve trust are really just a subset of situations that involve risk. So since risk is the broader concept within which trust is subsumed, it really makes sense to consider risk as the more fundamental concept, exactly like the research progressed. But now we should ask ourselves, is risk the most fundamental concept? And with that, I would say no, I don't think so. Because why do we even have risk? And I would argue that we have risk because there is uncertainty. If everything were certain, right, if everything were completely certain, there would be no risk. There would be no risk because I am certain about this. So if there's certainty, there is no risk. And if there's no risk, there's no need for trust. So I think we can take this logical progression and we can arrive at a conclusion that cybersecurity is fundamentally a problem of uncertainty. And you may be sitting there thinking, good, thank you. What do I do with that? And that's fair, right? And that's a great observation. But what I'll say is we can take this idea of uncertainty, and this becomes the foundation, right? This becomes the foundation upon which we start to build. And when we start to think about uncertainty and what we know about uncertainty and start to apply that to what we know or think we know about cybersecurity, this is where things start to get really interesting, largely because there is an existing extensive body of work that deals with the concept of uncertainty in physics. But to say that uncertainty is a fundamental component of physics and then also make the claim that uncertainty is a fundamental component of cybersecurity, therefore somehow physics and cybersecurity are related, well, that's not a sound logical progression, right? We would call that an association fallacy. So we can't just rely on that. So we need to dig deeper, and we need to understand what uncertainty that we're familiar with in physics, what that can tell us about the uncertainty that we know in cybersecurity. So to do that, I'm going to talk about a gentleman named Claude Shannon. So Claude Shannon is considered the father of the information age, right? And he wrote a paper in the late 1940s, and that paper was called The Mathematical Theory of Communication. And in that paper, what Shannon did was he showed us and actually proved how to optimize the capacity of a communication channel to transfer information from point A to point B. And in that paper, Shannon talked specifically about the idea of uncertainty. And what he said, what he told us about uncertainty was that uncertainty as a concept and the concept of information, specifically information, how Shannon defined it, are mathematically identical. They are mathematically identical concepts. And if and what Shannon told us is that in order to be able to measure this, we can use a generalized form of the equation for entropy, the same entropy that we're familiar with in physics. And if we go a step further, that same form of entropy, that generalized form of entropy, can be used as a measure of complexity. Now, if that seems abstract to anybody, it's because it is. It's extremely abstract. And I'm not going to go into the details of why, when we start to think about that, that really actually starts to make sense. But if you're interested, you have a homework assignment, and that is read about the thought experiment called Maxwell's Demon. And that thought experiment was posed over 100 years ago, but it really does a good idea at taking these ideas of complexity, uncertainty, information, entropy, and kind of making it into something that's physically understandable. But I'm not going to do that. Instead, I'm just going to roll with this idea that we now have a relationship between uncertainty, information, and complexity. And with that, I'm going to take a step back, right? And I'm going to revisit the question that I originally posed. Is cybersecurity fundamentally a physics-based problem? So what I've argued so far is that we can think about cybersecurity as fundamentally based in uncertainty, And we can think about uncertainty using what we know in information and complexity. And if we take a step further back from there, what I claimed is that security is the protection of value, the protection of meaning and value. So if we think about the larger picture of cybersecurity, we can ask, what is it that we're trying to protect? And I would argue that we're trying to protect information, specifically information that has meaning and value. Now, I don't think that that's controversial, and actually I don't even think that's all that interesting of a thing to say just by itself. But what we can do is we can take these ideas of information and complexity and we try to understand what those can tell us about the challenges that we're having in cybersecurity. And to do this, I'm going to go back to Shannon again. So remember what Shannon taught us. He taught us how to optimize the capacity of a channel to communicate information from point A to point B. And in order to do that, what he told us was that we need to ensure that whatever information is sent from point A has an equally likely probability of being received at point B, right? So if point A sends me a 0, right, the probability of me receiving that 0 needs to be the same as the probability of me receiving a 1 when a 1 is sent. And you can kind of understand why this would be important, because if we look up here, if we assume the characters A and B are represented by these binary strings here, if the probability of me receiving a 0 when a 0 is sent is different than the probability of me receiving a 1 when a 1 is sent, then the probability of me receiving the character A when the character A is sent is going to be different than the probability of me receiving the character B. Right? We need those to be the same, and we would call that, we need that channel to exhibit what's called a probabilistically uniform distribution, where anything that is sent is equally likely to be received. And in Shannon's thought process was that he was trying to optimize for anything to be sent. And in order to optimize for anything to be sent, I need to make sure that everything is equally likely to be received, a uniform distribution. So for those that aren't familiar with information theory, let me kind of explain that. So if you look up here, we've got, on the abscissa, you've got probability, and probability goes from 0 to 1. And then on the ordinate axis, you've got complexity, but complexity could also be, information, entropy. And what this is telling us is that if we have an event, and that probability of that event is it either is going to happen or not happen. It's either 1 or a 0, right? If the probability of that event is 0, then that doesn't provide any information. There's 0 information, because I know that the probability is 0, right? Sometimes we think about information as the amount of surprise that we get. There's no surprise. I know the probability is 0. That's not going to happen. The same is true if the probability is 1. The probability is 1. No surprise, right? Because I know the event's going to happen. So if there's no surprise, there's no entropy, there's no information, and there's no complexity. However, if the probability is 1/2, then I am equally unsure of if that event is going to happen or not happen. So that is maximum surprise, right? So that is maximum information, maximum entropy, but also maximum complexity. And the reason that this is important is because what Shannon told us is that in order to optimize the capacity of a communication channel, I need to design for maximum information, maximum surprise, maximum complexity. So, for those of us that are of the opinion that complexity is the enemy of security, this should hurt. This should be painful, because what this is telling us is that we have specifically and purposefully optimized our technology for complexity. That might be a bad sign, but don't worry, it gets worse. Because what Shannon was trying to do, right? Shannon wasn't trying to design for something specific. He was not trying to design for some specific thing. He was trying to design for the general purpose, for all possible things. And in fact, Shannon didn't care at all about the information that was being sent. He didn't care about the meaning of the information. And he specifically said that within the context of the engineering problem that he was trying to solve, that meaning is irrelevant. So understand that I'm pointing at Shannon, but Shannon wasn't the only one doing this of his contemporaries. This was actually done by a lot of people and is still being done. And it actually has a basis in philosophy that extends back hundreds of years. That's a story for a different time. But know that it wasn't just Shannon. It includes many names that you're probably familiar with, like Gödel, Church, Turing, von Neumann, many of the people that were instrumental in the early days of communications in computers. So when we think about this historical context, an interesting but pretty disturbing question arises, and that is it reasonable for us to believe that technology that was created with the assumption that meaning is irrelevant is actually going to be all that effective at helping us to protect meaning? And if we think about this in a slightly different way, we can ask the question, why, and I asked this question to myself, like, why is it so difficult to design technology that is just fundamentally secure? Like, why is it so difficult to design systems that are just fundamentally secure by design? So if there's merit to what I'm talking about here, the answer to those questions may be because we can't. Because the technology that we're using is incapable at a fundamental level of addressing security, because security is the protection of meaning, yet the technology that we're using to try to protect that meaning was developed with the assertion that meaning is irrelevant. I told you it was going to get worse, right? But don't worry, right? If that were the end of the story, then this talk would likely be in the running for the most depressing S4 talks ever. But that's not the end of the story. Because what I find particularly interesting about the history of scientific discovery is that when we discover a new field, say cybersecurity, we don't start in that field with a full understanding of the fundamental principles, right? If you've ever been to Istanbul, you drive through a part of the old city in Istanbul, and there are still these aqueducts that are standing, right? These aqueducts were built in the 4th century by the Romans. The 4th century was well over 1,000 years before Newton, his formalization of universal gravitation, mechanics, and calculus. So we don't need first principles to make progress, but the moment that we do have them, progress starts to happen much more rapidly. We learn as we go, we create theories, we test those theories, we refine those theories, we discard a lot of those theories, but eventually we end up with something that has some sort of fundamental representation of some phenomena. And so we take this idea and we think about potentially that the idea of meaning is useful and important in cybersecurity. Is there any research out there that is actually diving into these ideas and trying to extend them? And I would say yes, I think there is. However, I don't know that the researchers are really thinking about their research in this way. And the reason that I think that, in order to understand the reason that I think that, we need to spend a little bit of time and we need to talk about the idea or the concept of meaning and what makes something meaningful. And if we get too far into that conversation, you're going to have to talk to philosophers, you're going to have to talk to cognitive scientists and neuroscientists, not me. Like, I'm an engineer, so I'm going to stay in my lane here. But what we can do is we can take what these folks are telling us and we can start to apply them to our fields. And what we know, very generally speaking, about the idea of creation of meaning is that out of this sea of information that perpetually surrounds us, we create meaning by selecting particular things that are relevant to us. We can't take everything, right? We can't take every sight, sound, scent, and process it. There's too much. We can't do it. And I can't live my life assuming a uniform distribution where anything that could happen is equally likely to happen. That would just be paralysis, right? We couldn't do that. So instead, what we do is we take things that are relevant to us. And in that process, we are taking everything that could be, and we are pushing it up and we are constraining it to that which is relevant to us. So it appears that part of the process of making meaning is based on constraint. So if we think about this idea, how could we use this idea right now? If to build security into products from the very fundamental, from the very foundation means that we need to focus on meaning, then we may need to begin focusing on technology as a mechanism of constraint. And when we think about that, it's very obvious of all of these technologies that we've been using that are actually mechanisms of constraint. So perhaps Constraint is one of these things that we've always known, and maybe we now know why it's so important. So just to give you some examples of the idea of constraint in action, silicon. There are many companies out there that are designing their own silicon. Why? Why would somebody design their own silicon and not just take a general purpose CPU, plop it in, and code it? Well, when we design our own silicon, we're focusing on meaning. What do I want that chip to do? What do I not want it to do? We design our own chips because we want them to do what we want them to do, how we want them to do it. We are constraining what is possible within that chip. And we can go higher up the technology stack and talk about things like programming languages. And when we think about programming languages from the perspective of constraint, then it starts to make a lot of sense then why memory-safe languages seem so appealing. Because with memory-safe languages, we are constrained in how we can write code. And I would argue that you could write just as good a code in C as you can in something like Rust. There's just a whole lot more room for mistakes in C, specifically because of the lack of constraints. And then we can go even higher up the technology stack and look at devices. And when we look at devices from the perspective of constraint, then it makes a lot of sense why deny by default is so interesting, so appealing, because that device does nothing out of the box until you tell it to do something. You are constraining what that device does. So if information, meaning, and constraint do actually form the fundamental building blocks of cybersecurity, can we get to a theory that would allow us to create practical solutions that provide empirical results? And I think absolutely we can, but we have to remember that we're already using some of these ideas, but we're using them up at this higher level. And I would argue that we're essentially building on a foundation of sand, and that foundation is collapsing. So what are some of these ideas that I think are interesting? Well, there's one in particular that I'm really interested in, and it's an idea or a concept called semantic information. Semantics being the study of meaning. So what is truly meaningful about the information related to this system? What is truly meaningful about this algorithm that's taking these inputs to produce these outputs? And the general idea is that if we can start to optimize for meaning, then we can start to reduce the amount of information that doesn't provide anything meaningful to the system. We'll call this syntactic information. And when we reduce the amount of syntactic information in a system, we are constraining what can happen in that system, right? So if this is possible, if we can figure out how to do this, then the payoff in this case is that if I can fundamentally understand what is meaningful within a system and quantify that, as well as the amount of information, what is meaningful to what is not meaningful, then I can start to quantify, fundamentally understand the amount of uncertainty in a system. And when we understand the amount of uncertainty in a system, the systems that have more uncertainty have more risk. The systems that have more risk require more trust. So we can figure this out. We can start to understand the trade-offs between particular systems and technologies, and then potentially even understand the amount of uncertainty that we provide, potentially be able to understand the likelihood of failure of these systems. In other words, to truly engineer a cyber system. So if this is interesting to anybody out here, we would love the collaboration. So please reach out, right? Because this is a straight up, kind of in the weeds, fundamental research effort. But luckily, there's a field of study that's already looking at some of these things. And they have developed tools, right? And these tools, I think, can be helpful to us. And these tools have names like viability functions and transfer entropy and thermodynamic multipliers and conditional mutual information. And the field itself has an impressive sounding name: non-equilibrium statistical mechanics, or more generally, physics. So back to the question that I originally posed. Is cybersecurity fundamentally a physics-based problem? I don't know, but I think it's a fascinating question. And my hope is that now, maybe some of you do too. And if you do, please reach out, Because I don't know if physics is the answer, but we're going to have a lot of fun finding out. Thank you.